second theory that has to do with bonding. The first one was VSEPR, valence shell electron-pair repulsion theory, where the electron shells repel each other. The second one is valence bond theory. Now, valence bond theory describes covalent bonding through pairing of electrons in overlapping orbitals. And these atomic orbitals lie between the atoms. Okay, so when we look at this, electrons are in the atomic orbitals, and we're going to introduce hybrid orbitals, so it doesn't matter whether they're hybridized or not. The bonds result from the overlap of the orbitals. And the resulting geometry is going to determine the shape. So when we look at these orbitals, we've got to look at how they overlap. Well, if you look at an energy diagram, we've got the energy coming in the distance here. Basically, when you start with the two atoms held far apart, and as you get them closer and closer together, they start overlapping until they reach the minimum energy, which is the bond. It's the ideal bond. It's the lowest energy, most stable. And then as you keep bringing them closer together, it skyrockets, because at this point in time, what you're trying to do is overlap two nuclei, and nuclei are large, positive, dense. They're not overlapping. If you do that, as you get into nuclear chemistry and its fusion. So let's look at the overlap. Well, if you look at it, the s orbitals will overlap, and if you draw a line through the bond, you're going to get this circular overlap. So these are all circular. If you could read that, life would be good. Let me do circular overlaps. And this occurs here, here, and here. So what we've got is an SS. You can overlap an S, end on with a P, or you can have two end on overlaps of the P's. So these are sigma bonds, and sigma bonds have a set number of properties, which we'll get to in a minute. Now, the second bond that forms is a pi bond. We'll get to that again in a minute. But what it is a sideways overlap. So if you take a dashed line and run it through the overlap, what you get here is the side-by-side overlap. So basically, if you think about it, and the way I describe this in lecture when you can see it is if you put your hands together next to each other, you can rotate it without taking your hands apart. But if you put your fingers together and your thumbs together, form kind of a curve, you cannot free rotate your hand without breaking the bonds. So the circle allows rotation. The two circles, no rotation. And that's going to affect the properties of molecules, whether they can freely rotate or not. And a better representation of this is the end-on circular overlap. This is the sideways overlap. And something you're going to notice is this is on the internuclear axis. That means that this line lies directly in between the two nuclei. This one lies above and below the internuclear axis. So it's actually not directly between the two nuclei. It's between, the bond occurs between the two nuclei, but it's not directly between the two nuclei. It's above and below the plane of it. So that brings us to the types of bonds. Well, the first bond is the sigma bond. And it's a single bond involving two electrons from either hybridized or unhybridized. Wow, you can't read that. Unhybridized orbitals. It is the first bond to form. You will never form a pi bond, then a sigma bond. You'll always form the sigma bond. And the electrons are located on the intranuclear axis. Okay? The pi bond, on the other hand, is the bond formed in double and triple bonds involving only unhybridized p electrons. Okay, it is the second or third bond to form because a single bond is a sigma. A double bond is a sigma and a pi. A triple bond is a sigma and two pi's. We'll show you pictures as we go on this one. And the electrons are located above and below the intranuclear axis. Okay, so when we talk about bonds in valence bond theory, we're going to talk about sigmas and pi's. Now, that brings us to hybridization. Hybridization is the combination of atomic orbitals to form covalent bonds. There are some rules associated with hybridization. You cannot use them in isolated atoms. They're only used in covalent bonds. So if you have an atom just sitting there, you talk about the s orbitals, the p orbitals, and the d orbitals. You can't hybridize anything. Okay, hybrid orbitals have shapes and orientations that vary different from those of atomic orbitals. All orbitals in a set of hybrid orbitals are equivalent and form identical bonds. I'll show you this in more detail. That's the purpose of hybridizing, because then you get the identical. For example, if you think about, you've got to paint something, and you have 1 gallon or pint, let's go with pints, quarts. 1 quart of white paint, and you have 3 quarts of red paint. But it's going to take you a full gallon to paint whatever structure, and you don't care about the color. But you want the color to be uniform. Do you paint with the red and then move to the white? No. You just mix them all together, and that way you get a uniform color across the entire area. And it's not white and it's not red, but it's pink. Okay? The next rule is really simple, and when I ask questions, it trips you up. The number of hybrid orbitals has to equal the number of atomic orbitals used to produce. So if you combine 4 orbitals atomic, you're going to get 4 out in the molecule. You combine 10, you're going to get 10. You can't vary the number. Start with 8, you end up with 8. Okay? The type of hybrid orbital on a bonded atom depends upon the geometry of its unshared electron pairs and the atoms bonded to it. So one thing that you need to know, and this is jumping forward to this rule, is hybrid orbitals can either be occupied by bonding pairs, or it can be occupied by a lone pair. However, you cannot have hybridized orbitals if you're making pi bonds. They have to be unhybridized p's. But you could have a hybrid orbital that has a lone pair in it or a hybrid orbital that has a bonding pair. So I'll show you how that works as we go. So let's see some examples of why a hybrid orbital forms, how it forms, etc. So if we look at CH4 bonding, we know that there are 4 bonds. And we know in real life that they are identical. Okay? So if we were to look at them from an energy standpoint, and we were to take the S's from the hydrogen and combine them with the carbon. Well, first and foremost, if we look at the carbon structure, a bond forms when electrons are shared. We can only share this one and this one. So it only allows 2 bonds. But we know that carbon will form 4 bonds. So what do? We need to transfer the electrons from the S to the P. So we pop this one up here. And then we've got 4 areas that we can bond. So that allows 4 bonds. The problem is you'll have 3 of this energy and 1 of this energy. So they're not going to be identical energy. And we know that they have to be. So here we go. So we started here. This is our starting point that allows 4 bonds, but 3 the same energy, 1 different. And we know they have to be identical. So if we hybridize, that means we take our 2s and combine it with the 2p's. So we've combined 1 of these and 3 of these. So 1 plus 3 is 4. Then we'll end up with 4 bonds that are identical. So what we've done is taken 1 red or 1 white and 3 reds, mixed them together and gotten 4 identical pinks. And the beauty or goodness or whatever of that is we know that when carbon forms 4 bonds with hydrogen, all 4 hydrogen bonds are identical. And the only way to achieve that is with hybridization. Okay? So if you take the 1s orbital and you get the 3p orbitals, you started with 4, you're going to end up with 4. Remember, we started with 4, we'll end up with 4. And what it actually looks like is, remember, S's look like the circle and pi's look like dumbbells. So what we end up with is a dumbbell with most of its electron density on one side. So what that allows that to do is that hybridized orbital actually has a much better overlap than the end-on P bond, orbital. Has a slightly less than the S, but not a big enough difference. So this is what they look like. Do you need to reproduce this structure? No, but you may want to know that it's 2-lobed with 1 really big one. Okay, so when it goes to bond, what happens is hydrogen can't hybridize. It's just got an S. There's nothing for which it can hybridize. But the carbon has 4, so they're all sp3 hybrid orbitals. And the beauty of this is count the exponents. So how many sp3s do you have? 4. 1 plus 3 is 4. So because we have 4 to begin with and we end up with 4, so we end up with this hybridization. Okay, so now let's look at it again, except let's look at it where we involve a double bond. So if we look at our original pop-up where we have 2 S's and 3 P's, then if we have to have a double bond, then we have to leave 1 P unhybridized, because you have to have that for a pi bond. So then if you only hybridize the 1s orbital and the 2p orbitals, then you end up with 3 sp2s. again, count the exponents. So if you have 3 identical sigma bonds, then you need 3 sp2 orbitals. And remember, a double bond consists of a sigma and a pi. So again, if you combine them, you'll have a little more S character, so your lobe actually gets a little bit bigger here. And if you put the 3 identical lobes together, you're going to end up with a trigonal planar structure because it is trying to separate out the, it's still trying to repel. So again, if you look at a molecule where you have a double bond, you will see that the sigma bond, which is the involves the hybrid orbitals, will be on the intranuclear axis. And you'll notice that you have 3 of them. Those are the purple ones. So this one is hybridized, this one's a hybridized, and this one's a hybridized. Notice that the pi bond is not hybridized. It is not, it can't be hybridized because if it's hybridized, it cannot form a pi bond, which remember is above and below the plane of the molecule. This is the plane of the molecule. So what we have here is 3 sigma bonds and 1 pi bond associated with the carbon, and 3 sigmas and 1 pi. And they're not showing you the second lone pair in the oxygen, so I'm not going to go there with the oxygen. So remember, if you group 1 sigma and 2 pi's, you end up with 3 sp2s. Here's another variation of that. This one's kind of easier to see because in this one, they got 2 carbons instead of a carbon and an oxygen, and it allows you to see the fact that you actually have the trigonal planar in this area, in this area. And again, these are mirror images, so we're good. If you have carbon hydrogen bonding where it's a triple bond, then what you're going to have to do is in a triple bond, remember that you need 1 sigma and 2 pi bonds. So you have to leave 2 p's alone. These have to be unhybridized. So you're only going to combine an S and a P, which means you only have 2 identical bonds. So when you hybridize here, the lobe is even bigger, and when you combine the 2, they're going to go opposite each other, so it's linear because you only have 2 regions. So here is the triple bond. Notice the hybrid is right in here. This are the pi bonds. This is 1 pi bond, and this is the second pi bond. If you'll notice, these 2 are opposite here, and these 2 are opposite, so those are your pairs. And notice that the pi bonds are above and below the internuclear axis, and the hybrid orbital and the sigma bond is along the intraorbital axis. Say that fast 3 times. Okay, so what that is here's a different variation of this. This kind of takes it apart so you can see it a little bit better, but you still see all of the pi bonds. Now, what's this little structure here? Well, this is what we call a benzene ring. It looks like this. And what it consists of is a series of 3 bonds, 3 double bonds in a flat ring. So what ends up happening with these is this allows this pi system to interact with itself and set up the p orbitals. So these are unhybridized p orbitals. All the sigma bonds are with hybrid orbitals in this structure. So I'm not sure why that's in there twice, but it is. So when we look at this, and they set up the double bonds on top, as I said, it kind of forms what I like to call a raceway, a donut on top and a donut on the bottom. If we have the pi's not interacting, then they're localized. All the bonds and sigma bonds are localized. But if you get an array of pi bonds where they can interact with each other, then the electrons basically spin around in the raceway and they are delocalized. So up to this point, we've talked about forming 4 bonds, sp3, 3 bonds, sp2, 2 bonds, sp. Can't go below that. So that brings us to, what do you do if you have 5? So if you look here, you're going to count 1, 2, 3, 4, 5. Well, that means you've got 1 s, 3 p's, that's only 4, and so you're going to add 1 d. So that gives you 5 bonds. Now, when you're looking at the structures, it's easier to look at them as electron regions because a double bond counts as 1 electron region, 1 sigma bond. A triple bond counts as 1 electron region, 1 sigma bond. So when you hybridize, you're only counting sigma bonds. So this is the sp3d2. This is 1s, 3 p's, 2 d's. That means we have 6 identical bonds here. So if you're exceeding the octet, you involve the d's. You don't go beyond that, and you don't hybridize the d's until you've hybridized as many p's as you need. Okay? Now, this bond rotation, hybridization, movement, etc., is actually really critical for eyesight. They talk about rods and cones and what goes on there. So this is actually kind of cool, so you can look at it with respect to eyesight. Now, geometric arrangements then of hybrid orbital sets. If you have 2, it's linear again. 3, it's trigonal planar. 4, it is tetrahedral. And the hybridization schemes are located or associated with the electron regions. So we're back to trying to identify the hybridization in each of the groups here. Now, if you'll notice, these are the identical ones that we've done before, except for I've added one more in here, and it's the nitrogen. And so we're going to do that one first, because then I have, again, copied in what I did the last time, from the previous set, section 2, and then we'll do the hybridization. I've already done the polarity, and so that's in a different section, so this will add in the hybridization. So as I said, we have one new one, and it's the nitrogen here. And so if you'll notice, we have 2 electron regions around each nitrogen. So that means it's sp hybridized, because you get 2 sp orbitals. And because the other thing is we have a triple bond, which, remember, consists of 1 sigma, which is hybridized, and 2 pi's. And the pi's have to involve p's that are unhybridized. So we cannot include those. So if you're setting it up with your list, you have 1s and 3 p's, then you can only combine these 2. All right. This brings up a point. Somebody usually asks at this point or at some point in time along, why do you only have 3 p's? Why can't you have 4 or 5? Well, we're back to our electron configurations where we have S's only have 1, P's have 3's, D's have 5. So if we were to go into the D's, there are a total of 5 there. but we want to use our S's and P's up before we start into our D's. So let's go here and look at it. Now remember, I've added the polarity in the polarity section, so now I'm just going to look at hybridization. So we're going to do hybridization. We'll do it in the purple so it's different. So we're back to 3 electron regions, which means this is going to be sp2. We need 3 sp2 orbitals. We only have 3 electron regions. Here we have 4 electron regions, so the hybridization is sp4. Because that's 1s. No, there is no sp4. I just went through that with you, and you let me get away with it. You need 4 sp3 orbitals, because that's 1 plus 3, so that's 4 orbitals. Now, this octahedral one has 6 electron regions, so that's 1. That's another 3, so we're up to 4. So if we need 6, we add 2 D's in there. Here we have 5 electron regions, and remember, we don't care whether they're lone pairs or single bonds. We only care if they're double or triple bonds. So because of this, we don't care. It's 5 electron regions, so it's S, 3 P's, that's 4, D, 1 D, because that will give us 5 orbitals. Again, 5 regions, S, P, 3, D. Now, this one's a little tricky. So if we look at it, we've got 2 regions around the carbon. So if we only have 2 regions, that's sp. So the carbon is sp. The sulfurs are sp2 because they actually have 3 regions. So if we look at this has to be a sigma, this has to be a pi, this is a sigma, this is a pi. Since the carbon has 2 sigmas, we're only talking about 2 regions because we have to leave 2 P's unhybridized to form the pi bonds. And that's in the carbon. But in the sulfur, we only have 1 double bond and 2 singles. So that means we have an sp2 hybridization. So when you're looking at molecules, typically you only worry about the central one. I just want to show you that you can do the ones on the outside as well. All right, and hybridization can occur in ions, so we don't worry about the fact that these are ionic or not. We still have 4 electron regions. There are no double bonds, so it's sp3. In the next section, we have 6 electron regions, so it's sp3d2. Because that's 1, 3, that's 4, 5, 6. Yeah, we need 6 electron regions. So here we've got the electron regions, and we're good to go. All right, so let's take it on again to the extended. Now, this is identical to the one we did before, so we've done polarity on it. We've done bond angles. So we're really looking at hybridization. So the first one is C3. So if we look at it, there's 1, 2, 3, 4. So we have 4 electron regions. So that means it's at, whoops, I have no earthly idea where that 3 came from. So that means it's sp3. The oxygen here, remember, you have to account for the lone pairs. So here we have 2 lone pairs and 1 sigma bond, or 1 electron region. So that means that we have to have a pi bond, so we need 1 p unhybridized. So since we only need 3, we'll have an sp2. Now our nitrogen, we look at it and it has 3, right? No, don't forget the lone pairs. So it has 4 electron regions again. So that means it is sp3 hybridized. C1 here, if we look at it, has a sigma here and a sigma here. So it has 2 electron regions. So it can only have 2 hybrids, because these pi's have to be p's that are unhybridized. So what we're doing is 1s and 1p. And if it makes you happy to write the 1 in there, you can. You don't have to, so I'll write it as an SP. So that was actually not that bad. You will have an extended problem on there that will allow you to take it through into the next group. So remember, for hybridization, what you're really looking at is you're looking at the number of electron regions, the number of either single bonds, sigma bonds, and lone pairs. Those count as regions that can occupy hybrids. Pi bonds have to be unhybridized p's. So, oh, I forgot. This was the one that was added in. I accidentally added in a blank page, so we're just going to ignore that one. But one of the things that you need to consider is not only the hybridization of the central atom, but when you go to make up the bonds, you have to actually look at the hybrids of both. So chlorine, remember, will have 3 lone pairs. So the chlorine itself has 4 electron regions, so it's going to be sp3 bonded. Whereas the C3, that should have been a C4 because it's not connected to C3. So when you look at the C4, it actually has 4 electron regions as well. So it happens to be sp3 as well. So if we actually talked about the hybridization involved in the 2 bonds, we have an sp3 bond. If we look at C2 to C3, this one is involved in a triple bond. So the hybridization of this carbon is sp1 because it's only got 2 sigma bonds, so it only has 2 hybridized. Whereas this one has 4, so it's an sp3. So when we look at this bond, this then would be an sp bonded to an sp3. For the oxygen here, remember we have our lone pair, so we have 3 electron regions. So it's 1 sigma and 2 lone pairs. So that means we're sp2 hybridized. This carbon here is 3 sigmas and 1 pi, so it's sp2 hybridized. So this bond would be an sp2 sp2. Basically what this does is allows you to look at 2 molecules, because you're going to find later when you get to organic, this problem actually came from an organic chemist, is they're going to want you to look at what hybrids actually overlap, because the hybridization affects the energy, which when you overlap affects the energy of the bond. And that's an important feature. So it's not only important to look at it as a single atom, but how that atom interrelates to something else. Okay, so we finished the hybrid orbitals. We finished the valence bond theory. The last section is going to involve the third and last bonding theory.